just start pretty straightforward for us. All right, so what did you guys get for number 2? Sine squared of x. So in this case, so again, if I have this, in order to get sine squared of x, she took, so we have sine squared plus cosine squared equals 1. And so 1 minus cosine squared, we just move this cosine squared over, and it already matches. Wow, that doesn't look like cosine squared. Pretend. And so this is just going to be sine squared. Okay? Now, it does get a little more complicated right here, where I have now, it's cosine squared minus x. So in this case, if I have sine squared x plus cosine squared of x equals 1, what you guys do to make this work? There's a couple, like you can go one way or the other with this.
For number 3?
Yeah, what you do?
Take the sign onto the right side and add or minus the 1 on the
Okay, so what Luke said he did, he said he moved this sign over. And now if you did this in the opposite order that we're just about to talk about, it's okay. So then we had to move the 1 over. I probably would have done them in the reverse order just so that I could make it match first and then get that alone. But you end up with a negative sine squared of x. Now you might say negative versus positive isn't really a big deal. But if you're thinking about this in terms of money or slope or anything like that, that negatives and positives are a big difference in math as much as it's just one little symbol. It makes a difference. I mean, if we're, we won $1 million in the lottery versus we owe the state like $1 million, it's probably a big difference to us. If we're going on a bike ride and we're going uphill or we're going downhill, it's a big difference. There's an impact on that. So, number 4 is very similar. What'd you guys get? Yeah. Okay. Now, getting into some of these other ones, so now secant would tell me I need to look at my secant rule. So notice the formula with secant and the other two there, the second and third formulas are slightly different, and that's because they have different properties. So secant squared minus 1, I have to now look at the next formula down. So it's tangent squared x plus 1 equals the secant squared. So if I want this to match, I'm going to move this negative 1 over, so it just ends up being tangent squared. Now, the next one here, we have cotangent squared minus cosecant squared. What did you guys get for that one? Negative 1. So let me get you through that as well. So this, when we look at the next roll down, so I want those two to match. So I'm going to move this over first. If you didn't move this over first, that's okay. I just think it makes it a little bit more obvious of what we're up to here. Sorry, this is really struggling today. So this is cotangent squared minus cosecant squared plus 1 equals 0. So in order to get that to be isolated, we want just this. I'd move that 1 over, so it'd be a negative 1. Okay, secant squared minus tangent squared, what did you get there? Positive 1?
Yeah.
Oh, yeah, it is. Because, initially looking, I was thinking it was the same as this one. So again, just want to talk you through it so you guys can kind of see what we're up to. is that we have tangent squared plus 1 equals secant squared. So in order to make this work, I'm going to move the tangent squared over. So I have to subtract it. So secant minus tangent is just 1. Very good. And then cosecant minus 1 is going to equal, what's that going to equal? Cotangent squared? So I move this 1 over, so then this is just cotangent squared. Now, one of the things I want to point out with these rules is that notice some of these rules involve things that are being squared and some of them don't. So these squared rules only apply to functions that are squared. So sine squared plus, or sine plus cosine doesn't just equal 1. So just making sure you guys got that covered. Let me just write that out here. So this is not a true statement. It's missing the squares. So just because this works for squared does not mean it works for just a regular sine and cosine. It's just like saying Pythagorean theorem, a squared plus b squared equals c squared works for a plus b equals c. That's not, it doesn't work that way. So these are squared formulas versus it doesn't work for singular functions. However, these do work. So these don't work if they're like not squared. These do work if they are squared. So let me show you guys what I mean here. So if I have tangent squared theta, it's the same thing as sine squared over cosine squared. So these can be squared, these can be squared, these can't, you can't take the square root of them, or you can't change them to a different power. So that might be something worth writing down. So both of these two can be squared. You can like write them as a squared rule. Okay? So what we're going to do now is we're going to get into what we're actually using this for, how we're, like, the starts of our simplifying. That wasn't it. That was the homework. Yeah, that was it.
I'm so tired.
I'm impressed though, you guys. I mean, most of you guys seem to catch on with it pretty quickly. Okay.
Yeah, this shit
So,
like the first time I heard it.
So again, what we're trying to do here is I'm trying to get us started on this. I don't think the ones I chose today are the most difficult ones. We're going to make them more difficult kind of each day. But I feel like this is pretty straightforward, but this does kind of cover everything. I couldn't decide if we should just go with one type of problem to begin with at a time. I didn't do that. I'm like wondering if that was a bad decision. I mean, I've taught these before, but we kind of have thrown it, I've always thrown it all at once. So what I mean with these trig identities, we're going to talk about these fundamental ideas, the most important identities. These are statements that are true for all values of the variable for which both sides of the equation are defined. So basically there's no undefined here. All the values would work in a regular like trig graph. we're going to simplify these and try to rewrite them in another way. So when I say to simplify, we want the smallest number of trig functions possible. So when I say to simplify, like the least amount of trig functions as we can have. Does that make sense? Least amount?
Least amount?
It sounds like a dumb thing to say. I don't know. It sounds like bad English. So we want the fewest less than I have. Would be good. I want the least amount of terms, so I want the fewest terms possible so I can kind of combine things together. So I probably should have said fewest, maybe. We're going to use our list, so we're going to look at these like these salmon sheets a lot. Now, one of the things that you might end up doing is technically, we prefer everything to be in sine and cosine. That's kind of the ones we're most comfortable with. So if we can get everything down to sine and cosine. So I said sine and cosine are ideal. So typically that's what we're kind of headed towards. Not always. I'll kind of try to show you when we don't do that. And if you're stuck, one of the things to do is kind of use some of those rules we used before. So look for factoring. So you may need to factor. So factor, combine, that I spelled combine wrong. The board moving slowly, like my mind goes too fast and then I can't spell anymore. Like I'm trying to like keep going and then I'm gonna blame the board. Okay. So it says use the fundamental identities to get a simplified equivalent expression. Now, right now we're just multiplying, it looks like just gibberish. I'm multiplying cotangent, secant, and sine. Like right now that looks like just nonsense. However, grab your salmon sheet, and that's why I didn't staple these all together. We're going to use this over and over again. So, kind of question is, can I write cotangent using sine or cosine? Yeah, what does cotangent equal? Cosine over sine. So I'm going to change that to cosine over sine. Right now that might not sound like the best idea because you're like, wow, you just added another trig identity. But again, anytime you're kind of like not knowing what to do, sine and cosine are kind of a good place to go back to. So I'm going to write cosine over sine. So I made it into a fraction. How about secant? What can I do with that?
1 over cos.
It's 1 over cosine. Again, if you need your sheet, feel free to use that. Now sine is already like in its own forms. I don't know that I would switch that. I'm going to put it over 1, make it a fraction. Any thoughts? What can happen? They can all cancel. So what we find out here is that there's a cosine on the top and the bottom, just like we've canceled with our fractions before, we can just cancel those. We have a sine on the top and the bottom, we can cancel. So this whole nonsense, this cotangent times secant times sine, all equals 1. Yeah, not 0. When it cancels, it equals 1. That's common. It's okay. And so what I want to remind you guys is don't forget about the things you already know how to do. We know how to do fractions pretty well. We know that things, if they're on the top and bottom, can cancel. So this actually just equals 1. This is much simpler than if, like initially if I had said, hey, we're gonna do a problem, it's just, you know, the answer's gonna be 1, and then I showed you this, there'd be, I mean, just making that connection that those are gonna equal 1 is kind of crazy. All right. So the next one's a fraction here. I want to give you a minute because I know some of you guys, like, this seems very logical to you and others don't, but I don't want to, like, step on your toes if I don't give you a chance to try it at all. It doesn't, you don't get to try it at all. So look at this next one, see if you have make any headway on your own. If you don't, we'll talk about it. And sometimes it's just trying things. It's like a puzzle or a maze, you might get stuck and not be in the right spot. It's kind of like thinking ahead a little bit. So like, just whether or not it's, well, like, no, I mean, you're not in a bad spot. So the fact that cotangent, if I see cotangent and I see a tangent, I'd probably use this. Typically, cotangent, I usually end up using that one.